Hello guys, today we are going to see about a solid state part 2. What are all the topics we are going to cover in this part 2, Bravais lattice, a range of radius ratio and their rules, types of ionic crystals, packing efficiency that already seen in the last video, but hexagonal close packing and the diamond close packing is missed, that's why I have taken in this slide. And density of solids and properties of solids. What are all the properties is there? Under this property, electrical, magnetic and dielectric properties we are going to see in the solids. And the next one is Bravais lattice. There is a 14 Bravais lattices are there. See here 3, 5, if you keep on counting until this, you will get a 14 Bravais lattices is there with each crystal system. So 7 crystal system shows 14 Bravais lattices. So we need to memorize these, how to remember these. It's very easy one. See, in all the Bravais, all the crystal systems having a primitive crystal, okay, primitive is there for all the crystal systems. And except that, body-centered cubic crystal is there, body-centered is there, which are first 3 and last 3, you just keep it in your mind. First 3, body-centered is there. So, these are yes. Okay, body-centered is there. In the face-centered, first and third is there. And end-centered, third and third. Okay, third and third is there. This is the very simple thing you can easily remember it. You have to separate 3, 3. CTO, already I said in the earlier video also, CTO and RHM. Okay, in this one, body centered, all the first 3's are there, face centered, first and third, end centered, third and third. The next, radius ratio rule. In this radius ratio rule, this is the metal is cation, the cation which is assumed to be very small and it is surrounded by the anion. Okay, this is the assumption. Okay, this is the assumption. It's very small and it's surrounded by the cation. This anion. This anion is called as a coordination number or ligancy. Okay, coordination number or otherwise is called as ligancy. What is the rule satisfying these things? Okay, the first, the anion and cation, these two are assumed to be a hard spheres, always very close to each other, that is touching with each other, they are saying. Generally, they are not touching each other, but they are very close to each other, very close enough to be in contact with each other. Okay, and this cation surround itself with as many as anions. So each ion is tend to surround around its ions. Okay, the positive ion is surrounded by the negative ion, and the negative ion is surrounded by the positive ion. Why is it so? To reduce the potential energy, each ion is surrounded by its another ion, opposite ion. Okay, this tendency promotes this close packing structure. Okay, this close packing, with the help of this close packing structure only, we are going to radius ratio range. What is the radius ratio? The radius ratio is the radius of the cation divided by the radius of the anion. This is the rule. Okay, with the help of this formula only we are finding the radius ratio. Okay, radius of the cation divided by the anion. So if the radius ratio is small, the coordination number is also small. If the radius ratio is high, the coordination number is also high. That you need to keep it in your mind. See 2, here it's very less. 12, it's a 1. It's a whole 1. Okay. So, and configuration is given and example is also there. 2, 3, 4, 6, 8. According to this coordination number, this configuration will also change. If it is a 2, it looks to be a linear. If it is a 3, and it looks to be a triangle. If it is a 4, and it looks to be a tetrahedral, and if it is a 6 and it looks to be an octahedral arrangement, and if it looks to be 8 and it looks to be a cube, it looks to be a cube. Okay, and the examples also given. Next, types of ionic crystals. See, in these three are, these three are AB only. Okay, and these three are AB type. Okay, and the ratio is also 1:1, 1:1, 1:1. We can say it as AB type or 1:1 type. The example for a sodium chloride, the coordination number is 6.6 and number of unit present in that is 4 units. If you see here in this structure, this blue is a chlorine and this orange is a sodium ion. So each sodium ion is surrounded by 6 chlorine ion. In the same way, each chlorine ion is surrounded by the 6 sodium ion. So this we call it a 6:6 coordination number, and it's having a 4 unit cells. And in cesium chloride, this is also 1:1 type, but here 8:8 coordination number. Here 8 unit cells are there in this. Each Cl minus ion is surrounded by 8 cesium ion. Okay, the C in each cesium ion is surrounded by 8 chlorine ion. This is a 1, 2, 3, 4, 5, 6. Okay, upper 4, down 4. So 4 plus 4, 8. 8 unit cells are there. Here the coordination number is 8:8. Here number of units per cell, only 1 unit is there. Here zinc sulfide is a 1:1 type. Here the coordination number is 4:4. Here this is a sulfide, this is zinc. So 1 sulfide is surrounded by 4 zinc. In the same way, this zinc is surrounded by the sulfide. So this is 4:4 coordination number. Here how many units are there? Number of units, 4 units per cell. Here the calcium fluoride, this is 1, this is 2. So 1:2. This is AB2 type. Otherwise we can say it as AB2. The coordination number is 4:8. Some of the examples I've given, and number of units is 4 units are there. Here Na2O is 2:1 type. Otherwise A2B you can say. The metal is twice and oxygen is 1. So A2B twice you can say. This is called as antifluoride. I have given in the example as antifluoride. Antifluoride is Na2O. 2:1 ratio. So the coordination number is 8:4. The next one is packing efficiency. What is packing efficiency? I already said in the earlier video, the volume occupied by all the constituent divided by its volume of the unit cells. Here number of atoms is also there according to the packing crystals. Okay, here the hexagonal crystal close packing. In this 6 is the number of atoms. Number of atoms in this is 6 atoms, and 4/3 pi r cube is a volume and divided by the volume of the volume occupied by the constituents. Here 6 into this is the volume of the unit cells. Okay, the overall the packing efficiency of the hexagonal close packing is 74% as like of face centered cubic crystal. Okay, face and the hexagonal close packing is the highest one, that is 74%. The least one is a diamond cubic, that is DC. Here 8 atoms are present in that. The packing efficiency is 34%. Okay, the next one, density of the solids. How to find out the density? Density is equal to mass by volume. Here we have to find the density of the solids. So solids means mass of the atom divided by the volume. Okay, mass of the atom present in the unit cells and the volume of the unit cells. So mass means number of atoms into the molecular weight in AMU, atomic mass unit. Atomic mass unit, we have to write it in a kilogram. So 1.67 into 10 to the power of minus 27 kilogram divided by the volume of the unit cell. This is the formula. Okay, number of atom, molecular weight, that is converted into kilogram and divided by volume. Okay, this in general we can say the summation of number, which kind, that kind you have to write it, and the molecular weight of that kind divided by its unit cell, volume of the unit cells. Or otherwise the formula units you can say. If it is given in a formula, from that we can find the density. So in all the ways, the number you have to find out, and the molecular weight and kilogram, we need to convert it to kilogram, and the volume of the unit cell. This is the way we need to find the density of the solid. And properties of the solids. The first property we are going to see is electrical properties. This electrical properties is based on the conductivity. Okay, this is based on the conductivity we can say. Okay, the conductivity, what is the range of the conductivity? The range of the conductivity is 10 to the power of 8 to 10 to the power of minus 12 ohm inverse centimeter inverse. This conductivity we can classify as conductors, semiconductors and insulators. Mostly the conductors are metals and semiconductors are semi-metals. Insulators are non-metals. Okay, first we will see the conductors. In conductors, ions are the charge carriers and they conduct electrons. Okay, here the electrons from the valence bond, see here the valence bond overlap with the conduction band. So the electrons are travel from here to there. The energy, there is no energy difference, so easily they will overlap. Okay, this is the conductor. What are the, when it will conduct, when it is in a molten state, then only it will conduct. That is mobile ions. The mobility of the ions will be there, then only it conduct. Example is sodium chloride, potassium chloride. Semiconductors. What is semiconductors? In the semiconductors, due to the presence of the impurities and the defects, the electrons jump from the valence band to the conduction band. And by increase of temperature, it can easily jump from the valence band to the conduction band because of the energy gap is very less. Okay, so it is easily jumped. And the example is semi-metals. And insulators, there is a no conduction in the insulators. Insulators are non-metals. Okay, the energy gap is also very high. The conductivity is not at all there. This already is we can also we can say it as a forbidden zone. The next one is magnetic properties. The basic magnetic field, that we call it as a Bohr magneton. The value of the Bohr magneton is 9.27 into 10 to the power of minus 24 ampere meter square. Here you can see the nucleus is surrounded by the electrons. Okay, surrounded by the electrons, and it will create some magnetic field. Okay, it always surrounds the nucleus. The electrons is always surround the nucleus. It will create a magnetic field that shows the magnetic moment along the axis of the spin. So see here, the spin is also along the axis of the magnetic moment. So always, the direction looks to be like this. Actually, on the basis of this spin character, we can say it as diamagnetic, paramagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic, like this. See, for one substances is completely filled orbital and there is a no unpaired electron, means we can say that as a diamagnetic character. Okay, in that type, if you apply any external field, it shows very less repulsion. Okay, that unpaired electrons, paired electrons shows very less repulsion by the external magnetic field. The example is titanium oxide, sodium chloride, vanadium oxide, and benzene. And the paramagnetic, in this case, the materials shows unpaired electrons around the orbitals are not completely filled. These unpaired electrons are attracted by the magnetic field easily, by the external magnetic field. It's easily attracted, and it lost when the absence of the magnetic field. If the magnetic field is not there, it will lose it. If the magnetic field is there, it will get attracted. Okay. Example is oxygen, copper 2+, and iron 3+. Ferromagnetic. Ferromagnetic shows a permanent magnetism. Is always, you have to keep that in your mind. Ferromagnetic means always having a permanent magnetism. Whether it is a magnetic, external magnetic field is there or not, that doesn't matter. The permanent magnetic field will be there in the ferromagnetism. Why is it so? The spin, if you see the spin alignment is always in the same direction due to the same direction alignment. The permanent magnetism will always be there. Example is iron and nickel. Antiferromagnetism, that is the reverse of the ferromagnetism. This is also having unpaired electrons. You may think, we have to expect that it may be a paramagnetic or ferromagnetic, but it is not so in antiferromagnetic substances. Why is it so? That spins are opposite to each other. One is compensated by the other spin. Here the one is on the upside and another one is on the downside. So each one is compensated by each other. Okay, one is compensated by the other one. So here the zero net magnetic moment is there. There is no magnetic moment. The example is manganese oxide. And the last one, ferrimagnetic. Here it shows a very small magnetic moment. See, this is also in opposite, unparalleled and anti-equal, but it's the alignment is, see here, the alignment, one is a top, one is a down. Actually, it's a parallel, unequal, parallel, and anti-parallel alignment, and it shows very small magnetic moment. That is ferrites Fe3O4. The next one, dielectric properties. Dielectric properties, see here. What is dielectric properties? The electric field is generating. Okay. See, this is the nucleus which is surrounded by the electrons. This is the electron cloud. This is the nucleus. So this is this normal thing. Okay. The electrons which is surrounded by the nucleus. Before electric field, it looks to be like this. After electric field, what will happen? Here the polarization takes place. After applying the electric field, what is happening? This nucleus positive charge is moved towards the negative charge, that is the cathode, and the electron cloud, the negative charge, it's moved towards the positive charge anion. Okay, this is what, polarization. This polarity, according to this polarity, we are segregating this type of materials. Piezoelectricity, pyroelectricity, ferroelectricity, antiferroelectricity, and superconductivity. These polar crystals, after applying this electricity, these polar crystals we are classified as piezoelectricity, according to like this. Okay, the first one, piezoelectricity. When these substances, this piezoelectricity effect, when we will get, When the polar substances are subjected to mechanical stress, when they are underwent for the mechanical stress, there is electricity will be produced. That electricity we can say it as a piezoelectricity. Okay, for when the crystals, polar crystals are underwent for the mechanical stress. Even if you apply some external field on the polar crystals, then that time also what will happen? The mechanical strain we can observe it. Pyroelectricity. What is this? The pyroelectricity, when they will get the pyroelectricity effect, when the polar crystals are heated, it produces some small current. Okay, small current will be produces when the heat is applied to that. So that effect we call it as pyroelectricity. This ferroelectricity means this polar crystals is always, solids are always, we can say it as piezo. This ferroelectricity is always, we can say it as a piezoelectricity, but the reverse is not the true. All the piezo is not a ferro, but all the ferroelectricity substances is the piezoelectricity. Okay, so that we need to keep it in your mind, that ferroelectricity is always having some electrical effect. Antiferroelectricity. Antiferro means there is a no dipole moment. There is a no moment will be there. There is a no electricity will be there in that. Why is because of the already I said, and the magnetism also. Why one is cancelled with another one. So the both things will cancel with each other. The compensate with each other. The dipole moment will be cancelled with each other. So though there is a no dipole moment. For example, is lead zinchronate. Superconductivity. In this superconductivity, when the electrical resistance is zero, that time only the materials become superconductors. When the electrical resistance is zero, at the time it becomes superconductors. The temperature at which it becomes a superconductor, that temperature we call it as a transition temperature. The temperature at which it becomes a superconductor, that temperature we can call it as a transition temperature. The example is given below. Okay, this is the consolidated properties of solid. I already explained. Again, I'm consolidating. It's a map. It's a concept map. You can easily come to know. Three properties are there. One is electrical, dielectric, magnetic. Dielectric is divided into three: conductors, semiconductors, insulators. Dielectric properties is again classified as four. One is piezoelectric effect, pyroelectric effect, ferroelectric, antiferro, and superconductivity. Magnetic properties: diamagnetic, paramagnetic, ferromagnetism, antiferromagnetism, and ferrimagnetism. Thanks for watching. Subscribe my channel, click the bell button to get upcoming videos. Thank you.